I'd like to introduce, what I'm going to do is I'm going to introduce the people very briefly, because I think most of the members of the audience know all of the speakers, or almost all of the speakers. They're all absolutely first rate, and I'd like to thank you all speakers for coming, those who come from abroad, even those who come from Israel. I am very familiar with the traffic problems in Israel, so that's also quite an achievement. Charles Bennett is an IBM fellow. Don't underestimate that. We're all fellows of all kinds of things, but an IBM fellow is really a special honor. I remember when I was a PhD student at MIT, there was a paper published by 3 people, and there were stars near each of the names. The first author, there was a star, and it said, I think this was a DEC research postdoctoral fellow. 2 stars was Hertz doctoral fellow. And third author, it just said, jolly good fellow. And that was the way the paper was published. So Charles Bennett is a physicist and a computer scientist. It's tempting to say the best physicist among computer scientists and the best computer scientist among physicists, but he's absolutely an extraordinary scientist in both of these fields, and especially his work on the relationship between quantum theory and information theory. He is a member of the National Academy of Sciences for, I think, 1996 or 7. He's won the Wolf Prize, the Harvey Award, the Dirac Medal, and 4 honorary doctorates. And I'm waiting to hear about the connections between quantum theory, information theory, and the future.
Well, thank you. It's good to be back here. And I'm going to talk, in a way, I'll probably be preaching to the choir. The subject is the impact on technology, but I'm going to be telling you how important basic science is. I guess maybe I'll downplay that because you probably all agree with that. I'm going to be talking about the quantum nature of information, not only what can be done with it, but how difficult it is and how important it is to be able to understand it well enough to explain it at a dinner party. Now, I guess many of you who are in the scientific profession have the question, somebody asks you, well, what do you do for a living in 25 words? And so I think a good part of our duty, not only to inform the public of the importance of basic science, is also to be able to explain it to people in a way that makes it seem more approachable. Well, like other part of mathematics, informatics, which is the word, it's not much used in the English-speaking world, but in the Francophone world, for example, it's what means information theory and computer science, which are very much integrated now because the information infrastructure is part of the computer. It's a bit of an artificial distinction between information transmission and computation. But the information revolution that's still going on is based on some extremely brilliant and extremely audacious abstractions made in the 20th century. That if you had to associate them with 2 names, they would be Turing and Shannon. Turing invented a universal hardware-independent notion of computation. And this is, people, you might say his paper, which is almost unreadable. How many people here have read it? Turing, yeah. Okay, well, of course, yeah, but I think I only saw one hand. It's hard to follow. But okay, yes, three. Oh, of course, you too. I would have guessed. Anyway, but the average person who goes into a shop and says, "Can I get a program for that for my Mac?" understands what universal computation is. And Shannon, we understand that too. We understand about error correction and the capacity of channels, and it's become part of everyday life. By contrast, Well, I should say these people deserve much thanks for what the world that we live in now. But these notions were now known to be too narrow. And this subsequent incorporation of some essentially mathematical ideas from physics have led to a deeper and a more elegant theory of communication and computation. And I should say, in an audience, how many here people are computer scientists? All right, how many people are physicists? Okay, good. This is exactly the perfect sort. Some people raise their hands for both. Good, wonderful. Well, computer scientists they are a kind of mathematician, and they prove theorems, and they tend to have doubt the seriousness of physicists who don't. And like maybe even the ideas physicists are talking about are not really well defined enough to make any progress by trying to think about them without formalizing them a bit more. So it was a little bit of a shock when physicists came up with some ideas about information which computer scientists thought they already thoroughly understood, which turned in a certain sense to be completely fundamental. And that's what I'm going to be telling you about today. Well, of course, quantum effects were known through much of the 20th century, beginning at the beginning of it, but they were regarded by technologists and scientists of information as a nuisance. The theory of computation and of transmission of information, as developed by Shannon and Turing, concerned ideal computers, ideal channels, and when you had something that caused the equipment to become unreliable, for example, the uncertainty principle, then you use the tools of information theory and computation theory to remedy that imperfection. So quantum effects were thought of as a nuisance until rather late in the 20th century. And now we know that they also have positive consequences for cryptography and for computation, and ones that are still being discovered. So now, how do you explain quantum information at a dinner party to people who are, you try to get out, if it's a nice dinner party, you don't want to write on the napkin with your pen. And if you do, the people will stop listening to you pretty quick. So the best that I've come up with is to say that, well, of course, you don't have to explain every ordinary information because everybody uses it all the time. So you have to say, well, ordinary information is like the information in a book, and you can copy it and read it without disturbing it. And quantum information is more like the information in a dream. If you try to describe your dream, eventually you forget the dream and only remember what you said about it. And you can't prove to someone what you dreamed, and you can lie about your dream without being caught, except perhaps to your spouse. But unlike dreams, and despite the efforts of Sigmund Freud, there is a well understood theory of quantum information, much more so than of dreams. So what is the basic principle of quantum information? Of quantum theory is the superposition principle. It says that between any two reliably distinguishable states of a physical system, there's a continuum of other states that are not reliably distinguishable from the original ones. And that these behave like directions in space, where two states that correspond to perpendicular directions are reliably distinguishable, and any two states that correspond to non-perpendicular directions are in principle imperfectly distinguishable. And this, in a moment, I'll illustrate with the behavior of polarized photons, which is one of the simplest ways of showing this. But despite these differences, there are important similarities, which were not really noticed because the people who developed quantum theory thought they were doing something in physics and chemistry. They didn't think they were doing something about information processing. So this way of talking about qubits dates from the late 20th century, and it wasn't a word or a thought that occurred to Turing or Shannon or any of the people much before that. So just as all classical information is reducible to bits, and all processing of it can be done with operations on them 1 and 2 at a time, all quantum information is reducible to qubits, that is, systems with 2 reliably distinguishable states. And any processing on it can be done by operations on 1 and 2 of those at a time. And just as bits can be, are just as good, as I say fungible is a little bit of the abuse of the usual sense of that word, their value in computation is independent of their physical embodiment. You can make a bit 1,000 times smaller, and it's just as good as it was before, maybe even more useful because you can pack more of them into the same space. But if you make a car 1,000 times smaller, it's not good for much of anything. And in the same way, quantum information is fungible, and that means you can think about the processing of it in abstract terms without thinking of the physical system that embodies it. So this is a great degree of parallelism. And here I'll just illustrate some of the behavior of these quantum systems. So here's how you can use these. So this is a perspective drawing. So I'm going to use a horizontal photon here is there, and here's a vertical photon. And they travel along like that. And you can distinguish them because if you send them into a transparent body which has an anisotropic refractive index, like calcium carbonate, the horizontal ones will go this way. That is, it's not horizontal compared to the Earth, it's horizontal compared to the axis of symmetry of the crystal. And the vertical ones will be deviated while they go through the crystal and then come out in a different beam. So that means you can detect them as separate detectors, and you can use each photon to carry a bit. But if you send, of course, you can polarize them at any angle, or you can rotate the apparatus. If you put them in at a intermediate angle, instead of what you might expect of them being deviated by an intermediate amount, they behave probabilistically, and they go into this beam, become horizontal with this cosine squared theta probability, and into the vertical beam with the sine squared theta probability. So this means that you can use, if you have a stream of rectilinear, that is horizontal and vertical photons, you can distinguish them by this equipment, which I just showed you. Or if you know that your photons consist of 45 and 135 degree polarization, then you can rotate the equipment that's trying to distinguish them, and you can distinguish those 2 kinds of photons reliably too, but there's no way of distinguishing all 4 kinds. So that's the way quantum information behaves. Physicists have understood this for most of a century, more than a century now, but they thought it was something about physics. It didn't have anything to do with information processing, but you can see it does. And it's the basis of quantum cryptography. And I would say the first person who really grasped that this was a different kind of information processing was Stephen Weizmann, who is my colleague at Brandeis University. And in 1968, he wrote a paper about how you could use this imperfect distinguishability to make money that was impossible to counterfeit. The paper didn't get published until 1983 because he wasn't very persistent about trying to get it published. And then, using that same idea, Gilles Brassard and I promoted the idea of quantum cryptographic key distribution, which essentially uses this idea to allow 2 parties who communicate over a channel subject to eavesdropping and a public channel subject to complete eavesdropping to agree on a shared secret even though they had no secret initially. So that's just something that was, in terms of classical information processing, is not possible. But let's get back to what underlies this strange behavior. And this is, I found this also useful in dinner parties. this is due to Professor Bill Wooders in Williams College, one of my oldest and favorite collaborators. He's had a whole career teaching undergraduates, so he thinks a lot about pedagogy. And he said, well, really, there's a pedagogic analogy to the behavior of a quantum system when it approaches a measuring apparatus. The quantum system is like the student or the pupil in one of those old-fashioned schools. I guess the British schools were like that during the Victorian era, where the student was supposed to answer the question of the teacher but not volunteer information or start discussing something else in class. And of course the teacher is the measuring apparatus. So the teacher will ask the student a question and expect an answer from among the set of reliably distinguishable states. So the teacher says, is your polarization horizontal or vertical? And the pupil says, I'm polarized about 55 degrees. I believe I asked you a question. Are you horizontal or vertical? Horizontal, sir. Did you ever have any other polarization? No, sir, I was always horizontal. Now that's pretty strange. I mean, now how do we put the mathematics and physics into understanding that physical behavior, which is the way photons actually behave? I would say that the most remarkable consequence of this, which is even more strange, and we'll get in a minute to what Einstein thought of both of these ideas, is entanglement. So as I said before, quantum information processing can be reduced in the same way that classical information processing is reduced to bits, to processing of qubits by 1 and 2 qubit operations. So you can think of a quantum computer as having a bunch of wires which carry qubits each, and then inside it these wires interact by either gates that only affect 1 qubit, which essentially is a rotation of the direction of polarization, and wires that affect 2 qubits, and that's all you need. Now, the most simple and important gate that involves 2 qubits is what a computer scientist would call an XOR. And the quantum information theorists, because they discovered a new field, they thought they needed a new name for an old idea, which is sort of, people do this all the time, unfortunately. So they call it a controlled knot. But the idea is that if we use a vertical photon, we call that the quantum 1, and the horizontal photon for the quantum 0. If the control qubit is a 1, then the target qubit gets flipped to the, if it came in at a 1, it would come out a 0. So it gets rotated 90 degrees conditionally on this one being vertical. If this one's horizontal, the other one goes through without any change. But being a quantum computing element, it has to obey the superposition principle. And that means if I give a superposition of inputs, that is a direction that is a linear combination of horizontal and vertical, a diagonal direction, then the result of that gate has to be a superposition of leaving them both the same and them both becoming vertical. It's a superposition of these 2 outputs because you gave it a superposition of the inputs. Now, this entangled state, it behaves in ways that can't be explained by supposing that each photon has a state of its own. How many of you here have what you would call a basic fundamental understanding of entanglement? All right, that's good. Yeah, that's way above average. But it's an idea. Yeah, it's an idea this is something that is by now really well understood, except because Einstein didn't like it and science journalists are scared of it, you hardly ever find it properly described or explained when you read something. So, of course, they say rocket science is supposed to be the hardest science. You know, it's not rocket science. Quantum theory is the scariest science, and hardly anybody understands it. And it's our job to remedy that situation. So, if you wanted to describe this thing, you'd say that the 2 photons are neither one has a polarization, but they are in a joint state of sameness of polarization. And it is definitely not the same as each one of them being in a state intermediate between vertical and horizontal. And you can work out the algebra and see how that's different. Well, entanglement sounds like a fuzzy New Age idea, and I'm old enough to have actually been in San Francisco in 1967, which was called the Summer of Love. And you would often find people who were sure that they were perfectly attuned with you, even though you didn't have any ideas about anything, and neither did they. And they believed that if you had enough LSD, then everybody could be perfectly in tune with everybody else. They were not very good at mathematics. So if they had been better, they would have realized that entanglement is monogamous, and the more entangled two systems are with each other, the less entangled they can be with anything else. So let's discuss the monogamy of entanglement. And this is actually, I mean, of course, using that word is, of course, it's a metaphor. This is, although there was a kind of a performance art project in which in New York City a few years ago, where someone, a quantum optics person, produced a device that produced entangled pairs of photons, and newlyweds could go to it and in each one of them look at one of the photons for a brief few nanoseconds. They would be physically entangled. But anyway, just using this as a metaphor to help explain it at a dinner party. It's well known, you have this saying, I don't know if you have it in Hebrew, 2 is a couple, 3 is a crowd. You know, you see 2 people who are hitting it off especially well, and if you've got good manners, you'll leave so that they can go ahead with their relationship. So then this is also, I think, an unfortunate or maybe essential fact of human nature, that people enjoy being entangled, and some people like to try to get entangled in a non-monogamous way. So here we have Bob has become, you saw this, this is a controlled knot that is based on the state of Alice. The state of Bob flips from a 0 to, now they're in an entangled state. Now say Bob says, this is pretty fun, I'm going to go and try this with my friend Judy. And so he does the same thing here, hoping to be entangled both with Alice and with Judy. But what happens instead is that there's only correlated classical randomness between the two. They're no longer entangled. And if either one of these girlfriends leaves town, Bob's relation with the other one will be degraded to mere correlated randomness. But if they both stick around, he's entangled now not with either one, but with the non-trivial relationship between the two of them, which is an appropriate punishment. So now let's explain what entanglement has to do with quantum randomness. And this is really where this whole mystery of things that Einstein didn't like and that scares all of science journalists now. This is the nub of it, and it's not hard to understand. So let's look at this experiment we had before. We have these polarized photons going in, and they come in at an angle, and so some of them go into the upper beam, and some of them go into the lower beam. Now, suppose we don't actually count them, observe them. We just let them go into those beams, so they haven't actually interacted with anything. There is nothing in the physical universe that has witnessed that a particular photon is in the upper beam or the lower beam. It hasn't reflected off of anything. It hasn't been absorbed by anything. It hasn't been seen by anyone. And if no one observes them, this random so-called behavior can be undone. And that means if you put in a device here, which is called a half-wave plate, which changes vertical photons to horizontal and horizontal to vertical, so that's basically a kind of rotation of the photons. And then you put the two beams against another, I can't point with my finger, I have to point with this thing, another calcite crystal of the same thickness. The vertical photons will go, the horizontal photons will go on this path, and the vertical ones will go on that path, and they will rejoin and come out with the same polarization as they had before. So in other words, the idea that they behaved randomly is not completely right. If there was some witness to this separate behavior, it looks like they behaved randomly, but you can actually undo it. If you get rid of every record in the universe of what they did. So, metaphorically speaking, it's the public embarrassment of the pupil of having to say what his polarization is in front of the whole class that makes him forget it. Now, another way of putting this is maybe a slightly blasphemous way here, is to go back to this thing. The orthodox, the sort of, as Niels Bohr or anyone who understands quantum mechanics would say, it's not really correct to say that this photon went into this beam without anything ever having observed it. It went into a superposition of the two beams, and then it goes back into this beam. And what's happening in this part of it is the photon's position is entangled with its polarization. So the state of the photon along these two paths, it's in horizontal and in the upper beam entangled with the state of vertical and then the lower beam, and then you can undo the entanglement. Another way of looking at this is, I think, instructive. I think I said this to Danny Greenberger in the City College in New York. Or he said it to me. He said that when two photons go through an apparatus like this called an interferometer, and they rejoin and come out a definite path without anyone looking, even God doesn't know which path they took. And I said, well, isn't that a pretty blasphemous thing to say? He says, any God who would want to know, I wouldn't believe in that God. Okay, so entanglement is ubiquitous. Almost every interaction between systems causes it. So why wasn't it discovered until the 20th century? It's exactly because of this monogamy. Most systems in nature interact so strongly with their environment as to become immediately entangled with it, and that means the separate parts of the system only appear to be classically correlated with each other. Now, entanglement actually is responsible for the classical appearance of the world. So let's think of a typical situation in the world as some system which is interacting with an environment, but the environment is a special kind of environment. It has a lot of parts which don't interact with each other. A good example of that is all of the photons that are coming out of the lamps in this room, or if you're outdoors from the sun, bouncing off of us, recording information about us, going off into the sky, and not interacting with each other. So there's an automatic, massive replication of information which does what I just said. It makes the information public, and it destroys quantum superpositions. And this view of the origin of classicality is called quantum Darwinism by its inventors. But I think that's a bad name, because in Darwinism all the copies are descendants of each other, whereas in this process they are all copies of the same original, and I think it should be called quantum spam. So anyway, this is not characteristic of systems at thermodynamic equilibrium, but it's characteristic of the world that we're familiar with and live in, that there is something outside that's making lots of copies of the information in such a way as to obfuscate the other properties that the information might have had if it hadn't been being looked at. So I'm going to go back to the early history of this, and the Einstein-Bohr debate in the early part of the 20th century was about two things that Einstein didn't like about quantum theory. He certainly understood the mathematical consequences of it. He didn't like the indeterminacy, the fact that an identically prepared system will behave randomly. That, to him, it said there must be something about the system's original state that we didn't know. And the other thing was entanglement, which he called spooky action at a distance, or spukhafte Fernwirkung. He spent his remaining years trying to get a better theory, and I think what he wanted was that every effect should have a cause, not only a cause, but a nearby cause. And all of the physical theories up till then, including his own relativity, had that property. And I think he didn't see how you could have an orderly explanation of nature without it. But the rest of the physics community went on, and the slogan for that was "Shut up and calculate." I don't ask what it means; just say, does it give the right answers? Well, so Einstein, as I say, he didn't like quantum mechanics, and being the most famous scientist of the 20th century, it gave people a belief that they couldn't understand it either. And so I made a tweet about this because I was proud of being able to do a bilingual tweet. And I said that Einstein thought entanglement was spooky, but his wrong take on it as action at a distance refuses to die. And that's spukhafte Spätwirkung, that is spooky delayed action. Long after Einstein's death, people still don't understand entanglement. So anyway, lots of people began to not understand it, including some people who tried to patent it for communication with submarines and things like that. But this wrong idea is continually being rediscovered, like perpetual motion. So this is a good time to put in a kind of, let's say, I won't say comic relief, but a little bit of change the subject a little bit. But I think in science there are many kinds of crises. There are crises that lead to profound advances in science. There are the big one in physics now is quantum gravity, understanding how to unify quantum mechanics and gravity, which comes to a head in the black hole information problem. That is, if you drop some information containing thing into a black hole and then it comes out again, is the information lost or not? Now these in the history of physics, these are real crises where it looked like there was a contradiction, and in fact the contradiction needed to be resolved by some experimental or theoretical advance that led to great progress. This is the one that led to the special relativity. The solar neutrino problem was quite a more recent one. The sun was seemed to be producing a third as many neutrinos as it should be. And the solution of it was that there are three kinds of neutrinos, and they were changing one into another. They already knew there were the three kinds of neutrinos, but they thought that they didn't change from one into another, and they do because they have mass. And now the big one, and I don't know, I think it's pretty sure that some new physics is going to have to be discovered, or new mathematics to make sense of it, is the black hole information problem. Now, on the other hand, there are other kinds of, and I won't say this is a pure dichotomy. I think there are things that are intermediate between these two, but there are crises that are not crises of science so much as of human understanding and of ability to explain things in words. In other words, this crisis is gradually resolved by people getting used to the way things are, and this is the thing that Einstein was unable to do and other physicists were able to do during the 20th century. So, for example, I think I might say that those of you who followed my speech so far have an understanding of how entanglement makes sense in a way that it didn't seem to make sense to Einstein. Another example is how to irreversible behavior, such as the fact that you can't unscramble an egg, how can that come out of reversible laws of motion of elementary particles? And that's been resolved by a pretty thorough understanding of classical and quantum statistical mechanics and chaos theory and coarse graining. It's not something you can't explain. It's something that there are many different ways of explaining it, and they all sort of make sense. And the problem was that we didn't have the right language or a common language to talk about what was happening. The quantum measurement problem in Schrödinger's cat I think, is well on its way to becoming that kind of problem. It's a problem that is largely resolved by decoherence theory, and is now manifested in the relatively peaceful coexistence of the different interpretations of quantum mechanics, which means that quantum mechanics, when people do an experiment to test quantum mechanics, they always know what the result is going to be. And you can't really test one interpretation versus the other, which means that it's a question of people finding different language to talk about the same thing that they basically understand. Now, the very earliest example of this, I think, is the irrationality of the square root of 2, which I think was discovered when did Pythagoras live anyway? It was like it's 20 long. It's 2,500 years ago, roughly. So now this looked like a real problem, but now we've gotten used to it. Even though you might say that the word irrational number already, or similarly imaginary numbers, hints at how indigestible it looked at first, and now we've just gotten used to it. The problem was that we didn't find the solution; we just got used to it. So that's something to keep in mind. I said that quantum information theory is a beautiful and elegant enlargement of classical information theory, and that means that we have to explain what a bit is and what a gate is, a classical bit and a classical gate. A classical bit is a bit which has one of two standard orthogonal values, like spin up or spin down, or a vertical or horizontal photon. And a classical wire is a wire that conducts those faithfully but randomizes superpositions of them. And it does it for a very simple reason. It does it because it's interacting with an environment. So here we see that if a qubit interacts by means of this XOR gate with an environment in the 0 state, what comes out here is entangled if the qubit is anything other than a 0 or 1. So in other words, it behaves randomly if it's a superposition, but deterministically and gets copied if it's a 0 or 1. So that you can say a classical channel is a quantum channel with an eavesdropper, and a classical computer is a quantum computer that has eavesdroppers on all its wires. And when you build a computer, it's the fact that you don't shield the computer so perfectly that no information about what's passing through the wire leaks out of it, means the environment is an eavesdropper. And of course, this is bad for the secrecy of computations, but it turns out it's not immediately evident that it's actually bad for the efficiency of some computations. Some computations are a little bit like a person who says, I'm doing this hard math problem, and would you please stop looking over my shoulder because I can't think when you're looking at me. So there are problems like that. And of course, here's an example of one. This is a problem that was solved with a lot of effort by many classical computers working in parallel. That is to take this number and find its two prime factors, which, as you can see over here, are these two. Now, multiplication is pretty easy for a classical computer. In fact, even if you didn't have a classical computer, if you just had a quiet weekend, you could multiply these two and get this product. So you see, 3 times 7 is 21, so that's where this comes from. And then we carry the 2. So for a quantum computer, these two are not very different in difficulty to do. But for a classical computer, it's easy to do this, but hard to do that. I mean, easy to do this, but hard to do that. But in a quantum computer, and I've drawn it with sort of a double-walled box, because the idea in a classical computer, if you don't care about privacy, you don't care if information leaks out, but it leaks out. But you do not want information to leak in. Leaking in of information means that your computation is disrupted by the environment. And the whole purpose of a classical computer is to not have that happen. Quantum computer can leak in or out. Well, perfectly isolating a quantum computer from its environment is impossible. And so this whole idea would be impractical if there wasn't some kind of quantum error correction. And now, fortunately, the theory...
Kelly?
Yes. Oh, this is better, yeah. There was a... I thought you were going to tell me that I had almost no time left. Okay, this is much better. Can you hear me? Yeah, I love to walk around here. So there is a theory of elegant theory of quantum error correction that's been developed. It's a nice generalization of classical error correcting codes. And so you can take, this is sort of the simplest code that will preserve a single qubit against arbitrary error. You encode it into an entangled state of 5 qubits, and then you undo the encoding operation, and if any one of them has been disrupted, all the garbage goes into these 4, and the original comes out unharmed. And you can even make fault-tolerant quantum computing, which is based on the idea of error correction, in which you can tolerate even errors that occur during the error correction process. And so in principle, this is all very nice, except you need a pretty high reliability of the individual gates compared to what you would need for classical computing. And we're at the point where it's very hard to get close to that threshold. And even if you get close to it, you get a tremendous overhead from error correction, which I'll talk about more later. So now, quantum computing, we have got lots of quantum computers around the world. They're all pretty rudimentary. Here's one at IBM, and these are based on superconducting circuits at low temperature. And there are also in many laboratories all over the world. And not only superconducting quantum computers, but lots of different kind of physical systems which in one way or another give rise to a system, a degree of freedom that can be almost perfectly isolated from the environment and still allowed to interact with other degrees of freedom in the quantum way. I one time joked that quantum computing was a big boon for physicists because a physicist who had practically any kind of equipment in his laboratory could apply for a grant and say that it was something that could be used for a quantum computer. I mean, these are all pretty serious proposals for how to do it, and it's not even clear. I mean, I think what is clear is that ultimately when a really good quantum computer is built, it may involve several of these kinds of things to work properly. So if you talk to a layperson, they'll say, well, we've got this problem in computer technology that Moore's law is coming to an end. What are we going to be saved by quantum computers? And if so, how soon will we have them? Well, the first answer to that is no, because even if we had a fully error-corrected quantum computer, it wouldn't be able to do all computations faster, just a few very interesting computations, but not all computations. So get used to the fact that Moore's law is going to end. And then there's another, so here's the resulting is now well-developed theory of quantum complexity classes. So the next thing is this, the more bad news is that it's going to be very hard to make a fully error-corrected quantum computer. So what can we do? Well, certainly we can do quantum cryptography over very long distances, as the Chinese have shown with this satellite from a couple of years ago. Improved measurements and timekeeping, things that we already have from understanding quantum information. There's a lot of effort to prove that a quantum computer can do something a classical computer can't, even a useless thing. But that, to me, seems pointless because there's not a good reason for not believing in quantum mechanics. And then I will go now to a few things that we can do, maybe in the short run. But the best reason to study quantum information is basic science, and I think the most exciting reason for it is that it might solve the problem of quantum gravity. So we'll go quickly through some of these things. So I already mentioned long-range quantum cryptography is already something that can be done. It may be very expensive and a very low data rate, and there's only a few things you might want to use it for. And maybe I would say the Chinese are developing it because any other kind of cryptography that they tried to sell the world, people wouldn't trust it. Not that they should trust American cryptography. Well, anyway. So then there's the idea that if you could keep a quantum computer from decohering for just a few steps, maybe 10 or 15 steps, you could prepare an entangled state that might be useful in finding the lowest energy state of a molecule or some other moderate-sized quantum system whose full state space was classically intractable. And there's been some progress on this, where if they try to simulate a 3-atom molecule, they get the classical results are down at the bottom curve. The quantum results, the raw quantum results are up there, not as good, but doing the best in terms of error mitigation, they can get them to be almost as good. So it's not ready for use yet, but maybe if the quantum computers get a little better, it'll begin to be useful. Here's another thing that's very sexy, applying it to machine learning. And the idea there is to separate some data in a large dimensional space into 2 classes. And sometimes you can't do it because you can't do it by a linear hyperplane, but if you apply a nonlinear function to it and then try to do the separation, you can get it to work. And it's something that may also work with quantum computers, we don't know. But I think the most exciting thing is application to the quantum, quantum black hole problem. And this is a slide from John Preskill. He gave this example. This paradox led to the end of classical mechanics and its replacement by quantum mechanics. And this one is still unsolved. Where is it going to lead? Hopefully it'll lead to a consistent theory of quantum gravity, which we don't have yet. And he thinks that, and this is something that actually has to do with Technion. This third guy here is a professor, was a professor at Technion, Rosen. And his paper, famous paper with Einstein about entanglement, the same year he had another paper about something in general relativity that it allowed a solution where 2 wormholes, which at each end looked like a black hole, were actually separated by a neck that was growing at the speed of light. And this appeared to make no sense, but people are seriously thinking about it now, to the point where one of them said, this is the time for quantum information theorists to jump into black holes. And let's see. So here are my conclusions. Quantum information is a coherent basis for the theory of computing and communication and interaction between physical systems. A classical communications channel is a quantum channel with an eavesdropper. A classical computer is a quantum computer with eavesdroppers on all its wires. It has applications, and it may speed up some computations, but that's not really it's worth doing all this stuff, and there may be some great improvements, but I think the biggest thing it does is it shows us some way in which the world is simpler and stranger than we imagined before. And I would say it's so important that, like the roundness of the earth, it's something that should be part of every educated person's liberal arts education. And it can be explained and made comprehensible and fascinating. Thank you.
We have time for a couple of questions. Moshe.
What is your take on the D-wave machine?
I think it decoheres pretty quickly and hasn't. Oh, I need another one.
Yeah, here. No, you speak. That's the slides. She wants to give this to the people who ask the questions.
Oh, you give it to the people who ask the questions.
Yeah,
I can say it
over here.
Yeah, okay. And there's another one? Okay.
Entanglement.
All right. Oh.
Repeat the question.
Oh, what did I think of the D-wave machine? I think they're trying to use it for some kind of optimization problem, but it's a little hard. I should say I'm not at the forefront of critiques of the D-wave machine, but I think it's a little premature to call it a quantum computer.
Any other questions? Okay, thank you very much, Charles.